having spent a bunch of time thinking about the different ways that we can alter the heat transfer that happens through objects and what the heat transfer through an object depends on, it's key to recognize a specific fact, one which is probably already clear to you either from previous lectures or because you've just caught on to it. But there's a key observation about the relationship between the heat transfer rate and the surface area of an object that allows us to begin to think about engineering systems, about designing their shape in such a way that we can enhance heat transfer through them. Okay, so here's a simple example. Let's suppose that I have some kind of CPU. Okay, my very simplistic rendition of a CPU. There we are. And this CPU is taking electrical energy, and then in the process of doing computations, converts some of it to thermal energy. All right? That thermal energy manifests in the form of a volumetric thermal energy generation rate inside of the CPU. That causes the temperature of the CPU to increase up until a point where the amount of energy that the CPU is emitting into the air or its surroundings per time, that amount matches the amount that's being generated, the rate of thermal energy that's being generated inside of the CPU. Okay? Now, one of the things that we want to try to do when it comes to CPUs is to minimize the operating temperature of the CPU. The more you ask it to do, the more energy it requires, the higher the steady state operating temperature of it is going to be. And if you make that operating temperature too high, the electronics start to break, right? You literally start to observe mechanical failures in the components of the CPU. So it is to everyone's convenience that we try to make the operating temperature of a CPU as small as possible, because that will simultaneously allow us to do more things with it and also prevent it from breaking. Now, how can we do that? Well, we can do thermal energy balance. So if we consider, and pardon me, this is a kind of a sloppy drawing, but the whole idea is that this is supposed to be around the entire CPU, right? If we consider the CPU to be our system, then we find that Q dot times the volume, the energy that's being generated inside of the system, this has to match the heat transfer rate out. Okay? That's just a mathematical version of what we had stated before. And if we assume that this CPU is surrounded by air, okay, that this thing is kind of like hanging off of one of the sides, we don't have to be too specific about the infrastructure, then we would find that this Q is a convective heat transfer rate, right? That the heat fluxes out into the air are convective. And the way that we model that, at least the way that we've been modeling it so far, has been to say, well, there's some heat transfer coefficient multiplied by a surface area over which the heat transfer actually takes place, and then multiplied by difference in temperatures. In this case, the temperature of the CPU, or the temperature of the CPU at its boundary, and the temperature of the air surrounding it. Okay? And so, once again, if we want to try to enhance this Q, what are the different things that we could alter? Well, we can't really adjust the delta T. I mean, sure we could, but adjusting the delta T requires air conditioning. Basically, we have to lower the temperature of the surrounding environment, and certainly that will work. But it's not intensely practical, okay? So this will work. Increasing the temperature difference, like lowering the ambient temperature, will make the heat transfer rate out of the system larger. It will accomplish what we want, but that's not really the direction that we want to go to. Similarly, if we increase the heat transfer coefficient, we would also be able to make the heat transfer rate increase. But that's something that we don't really have the tools to discuss, at least not until we start talking about convection, right? Which means that we eventually will start talking about how we find these H's, okay? What I really want to focus on is something easy, something simple, something that we, for the moment at least, know that we can change, which is the surface area. So how could we do this? Well, the important thing to note, right? If we increase the surface area of contact between this CPU and the environment, then the heat transfer rate should go up. Let's take a look at a singular side. Okay, so I'm just going to consider this is just one wall, one little edge of the CPU. And so we expect to have heat transfer that's going, from here outwards into the environment. Is there a way that we can increase the surface area of this without necessarily having to fiddle around with what the actual shape of the electronics inside of the CPU is? Sure. What if we just go into a machine shop and we manufacture, some metal thing, and then we glue it to the surface of the CPU, and it's manufactured such that it has a larger surface area than this wall, okay? So what if we make something that looks like this? So once again, this is a horrible drawing, so I apologize. But we just kind of attach this plate, and then on this plate, this plate has kind of a fin sticking out of it, okay? And the reason that this is useful is because the addition of this fin gives this object more boundary surface area, which increases the value of this, which, hypothetically speaking at least, increases the value of this. Now, adding something like this from such a simplistic perspective seems like it's an easy win. But we also have to consider that the moment that we start messing around with the geometry of the system, we're also going to start messing around with a bunch of other things. For example, the H is understandably going to change. Remember that the H contains all of the physics we don't know about. And so you would expect that if you add a fin to a geometry, that the H is going to change. One obvious way to see that this is the case is that you can imagine that if there's airflow happening past the edge of the CPU, that airflow is going to change as a result of the fact that now there's this fin in the way, okay? Which will absolutely alter the H. So it's not quite as simple as just going in and adding surface area, but it's close to that simple. And you may also ask yourself, why stop at one? Why don't we just go and maybe add another one right on top of it, right? Where's the harm in that? And why don't I just keep doing this over and over and over again? And eventually, if I do keep doing this over and over and over again, you see the familiar shape of a heat sink that is usually attached to CPUs and GPUs and high-performance computers to start to show up, okay? And this object is called a fin. And it's kind of obvious why it looks like a fin in this way, but a fin doesn't actually have to look like a fin. A fin could also look like a pin. I feel like Dr. Seuss. But consider this little scenario, right? So we could also just have a little cylinder. And these are called pin fins. And remember that the only point of adding these objects is that we're adding extra surface area between the object and the environment. Okay? And so abstractly, any object that we add to another object to enhance the heat transfer via an increase of surface area is what we call a fin. Okay? And there's a couple of different ways to characterize how good a fin is. All right, so we can say the following. Well, what is the heat transfer rate that's happening through the object when we have the fin attached versus the heat transfer rate that's happening without the fin? So this is a very pure and obvious way of knowing whether or not the fin is good, because we are just relating how much the heat transfer rate goes up. Like how big is the improvement of the heat transfer relative to the base rate with and without the fin. And we usually call this the effectiveness, right? It's a unitless number, right? Because it's the ratio of heat transfer rates. And like I said, all it is the ratio of the heat transfer that's happening through the finned system to the heat transfer rate that's happening in the base not finned system. And so the higher this number, the better. And although technically speaking, this number can't be infinitely high, right? That would imply that this has to be infinitely large. You can imagine that this thing can potentially get like pretty big, right? For really well-designed fins. There's no theoretical limit to what this effectiveness is. And because there's no theoretical limit, even though it's a very concrete way of characterizing, you know, how good a fin is, this effectiveness epsilon is sometimes doesn't contain as much information as we'd like it to contain. What we might consider doing in order to add kind of like a bound to our measure of goodness for a fin is we want to maybe try to come up with some metric that has a maximum of 1, okay? And that metric is going to be the efficiency, which we're going to represent with an eta, okay? This eta is just, perhaps unsurprisingly, the heat transfer that's happening through the fin system divided by a maximum ideal value of heat transfer that could be occurring through the fin system. Now, you may ask yourself, well, what is this ideal scenario? Take a look. One of the things that's important to consider about the adding of fins is that the moment that we start adding fins, the heat transfer throughout the system is going to become far more complicated if we want to at least describe it with high resolution. For example, if we go back to the system that we were talking about before, this drawing is going to be extra bad. But if we go back to the fin system that we were talking about before, think of specifically only the fin, okay, of this little thing extending. If we wanted to analyze the temperature in this little slab right here, this little chunk, you would expect that there's heat transfer that's occurring through the fin, right? That's moving left to right, assuming that the original heat transfer was left to right. And because there's heat transfer that's happening left to right through the fin, then there has to be temperature differences through the fin. This can't just be a uniform temperature. And so you expect the temperature of the fin close to the surface to actually drop as you start going further and further out towards, you know, the environment. And the reason that this matters is that, remember that the heat flux through every point on the fin is determined by a heat transfer coefficient times the delta T. If the temperature of the surface starts to drop, the delta T is going to drop too. And so the heat fluxes at the end of fins usually tend to be smaller than at the base. Okay? And so now that you know this fact, what is the ideal fin heat transfer rate? Well, the ideal fin heat transfer rate is assuming that the temperature everywhere on this fin is the same. So we ignore the physical reality that in order for this to work, the temperature has to change on the fin. Let's just pretend like the temperature on the fin is the same everywhere, and then define this Q fin ideal as being H times AS as just T of the base. Here we go. So this ideal heat transfer rate is the heat transfer coefficient times the area, the surface area through which heat transfer takes place, which is of course the area of the fin, times the temperature of, pardon me, big mistake, delta T is equal to the temperature of the base minus the temperature of the environment. So what is the ideal heat transfer rate through the fin? Well, it's just H times the area of the fin surface times the difference in temperatures between the base and the temperature of the environment. Okay, so this temperature, this T base, we take it to be the temperature of the stuff that we're attaching the fin to. And then when we do this, when we attach it to this equation, we'll always find that this heat transfer rate Q fin is smaller than this because of the fact that the delta T drops for each individual like little chunk of the heat flux that eventually gets integrated up into this. That delta T drops. It's never going to be bigger than this delta T, okay? And so as a result, this efficiency behaves like an efficiency in the sense that it has a maximum of 1. And so why does it matter to have these things in place? Like, why does it matter to know what the effectiveness and the efficiency of a fin are if all that I care about is the process of enhancing heat transfer, right? If this enhances heat transfer, why don't I just make every surface a fin surface, at least when heat transfer is involved? And the reason is a little, quotidien. It's just manufacturing. It's effort, right? Like, does it matter whether or not we add a fin to a surface from the perspective of heat transfer? Well, it's usually always going to make it better, but how much money do I actually have to spend at the machine shop to make God knows how many fins, right? Is the energy savings that I get by attaching a fin to a surface more or less than the amount of money that I'd have to spend to get somebody in a machine shop to manufacture, however many fins we need for a particular system? And usually the way that engineers make these choices is by checking the effectiveness and the efficiency of these fins and then designing them such that the fins are worth it, or just saying, well, fins aren't worth it, so who cares? And so this is why you don't see fins everywhere in surfaces where heat transfer occurs, but you see them in quite a lot, whether or not they look like fins or not. And so we can use these things to make decisions about engineering systems, not just from the perspective of analyzing how they behave, but actually trying to govern how they work, of how we determine whether or not we want the system to be more efficient at the risk of increasing complexity of the shape.